process we can go through to optimize the cam tuning or cam timing under part throttle conditions. This will be applicable to continuously variable cam control engines. For this, we're using our Subaru STI with our Haltech Elite ECU fitted. And while we are running quad variable cam control in this particular engine, for the purposes of our demonstration here, just to keep things a little bit simpler, we will be focusing only on modifying the inlet cam position. Before we get into the actual tuning process though, let's jump into our ESP tuning software. We'll have a look at our setup and some of the key metrics we're going to need to keep an eye on. So we are currently sitting on our cam tuning tab here with some of the relevant information that we need to monitor. In particular, we've got our cam timing target table here displayed numerically on the left hand side, and it's always a good idea to keep a graphical display of this as well. Much easier to pick inaccuracies or errors in our trends if we're looking at them graphically as opposed to numerically. At the moment, we've got a table that is already relatively tuned, and we're going to zero that out. But before we do that, just looking at this table, we can get at least an idea if our cam targets are in the ballpark, because we know that there will be some normal trends that we're going to see. Looking at our intake tab, intake cam timing here, we know that typically in the idle areas and at low RPM, we're going to be at maximum retard. We can see that in the idle area and down at low RPM. Then as we move towards peak torque, we are going to see the cam timing advance. We can see there once we're in positive boost, we're running at about 45 degrees, which is getting close towards the maximum advance value that the cam can provide mechanically. And then as we move higher in the RPM, we can see as we get out towards the rev limiter, we've retarded back to the maximum retard value. So this is indicative that this cam timing table is probably in the ballpark. Likewise, we can expect that down in the low load areas in vacuum, we will have the same general trends, but a little bit less advanced than we have at wide open throttle or on a turbo supercharged engine out into positive boost pressure. So looking at this, we know that we're probably at least in the ballpark. Looking at graphically as well, we can see everything is reasonably smooth. We do have a couple of areas that I would definitely be revisiting, particularly this cell here, where we can see that we do have a bit of a hole in the map, and that's actually because we've been doing some tuning on that particular spot, as we'll get into. But if we have a reasonably generally smooth trend, that's typically what we'd be expecting from this table. All right, so that's our cam target table. What we're going to do though is actually zero this out. We're going to start from zero values, which is where we would be getting started. The next thing we're going to talk about is what's actually going to change. So of course, as we change our cam timing, we're expecting our volumetric efficiency of the engine to change. And as we've discussed in the body of the course, if we don't do anything about this, we're going to see that as we change our cam timing, the air-fuel ratio is going to wildly fluctuate. Now, there's a couple of ways of dealing with this. We can make iterative changes back and forth between our cam timing target and our main fuel table. Looking at that, obviously here we have our cam timing table. And if we move up, we've got two options here. We can just click on our fuel base, which is our VE table. That will then fill in the VE table here. So we can move backwards and forwards between these two tables inside of our cam tuning tab. We'll come back to our cam target, or alternatively, we've got another tab set up here for our more fundamental tuning functions, which is called main. We can click on our main, and at the moment that's showing ignition, but we can change that to our base fuel. So we could tune between those two tabs. And ultimately, we will be needing to make some changes to our VE table. But while we're getting started, we've got no idea initially where our cam timing is going to be. So if we've got the option, one of the nice functions that a lot of ECUs offer is closed loop fuel control or auto tuning. And I've got that set up. So we've got the values here on our main fuel, our main tuning tab. We've got our target lambda and our measured air fuel ratio. Let's head back to our cam tuning tab. And we've got another tab that I'm displaying here, which is our O2 bank 1 short-term fuel trim. So at the moment at idle, it's actually disabled, so that's not doing anything. Once we get higher in the RPM, we're going to find that the short-term fuel trim is going to make adjustments to our overall fueling in order to get our air fuel ratio onto our target. Given that the first cell that I'm going to tune here is in the cruise area, we're targeting the stoichiometric air-fuel ratio, and I'm not going to change that. It would be unlikely that we're going to need to change our target air-fuel ratio as we change our cam timing. It's just a case of changing our fuel delivery or our VE table to achieve that target. So this is a nice feature here, is that the closed-loop fuel control is going to do that heavy lifting for us in the background. And it's also actually going to help us with our cam target tuning. Because what we're trying to do here, if we want to make peak power or peak torque, basically they both occur at the same point at a fixed RPM, what this means is that we want to optimize or maximize the volumetric efficiency of the engine, maximizing the cylinder filling. So what we're going to see is that as we move from an incorrect cam target with low volumetric efficiency towards our optimal cam target where we're maximizing volumetric efficiency, we're getting more and more air into the cylinder. Now, of course, because we're operating in one fixed cell in our volumetric efficiency or fuel table, we're injecting exactly the same amount of fuel. So as we get our cam timing into the ballpark and we optimize our volumetric efficiency, what we're in turn going to see is that our fueling, our air-fuel ratio, will start to move lean. Now, of course, here in closed loop, the closed loop fuel trim is going to be increasing in order to correct that and get us back on our target. So what we can actually do is just take note of what's happening to our short-term fuel trim. Generally, what we're going to find is that the area where our maximum short-term fuel trim occurs, this is where it's adding the most amount of fuel, which in other words means that our air-fuel ratio without that trim would be leanest. This will also coincide pretty closely with our maximum or optimal cam timing, giving us peak power and torque. Now, that is not the only consideration though. What we'll typically find is that particularly under cruise conditions where fuel economy is a consideration for a street-driven car, we're probably going to find that we're going to make pretty significant or pretty comparable torque values across a reasonable range of cam timing values. So what I mean by this is we might see the torque within plus or minus about 1% across a range of maybe 10 degrees of cam timing. And what we can do here is choose to maybe not go for our optimal or peak torque value and instead drop that back maybe 1% in order to actually end up with improved fuel economy. So again, watching what our short-term fuel trim is doing, that's going to help guide us with that. Now that might all sound confusing, but it's all going to make perfect sense once we get started. So what we're going to do here is just begin by tuning a single cell. We're going to tune our 3000 RPM minus 20 kPa cell. Typically, once we're getting started though, this would be a process we'd follow very much like the HPA 10-step tuning process for an aftermarket standalone ECU, where we would typically start from low load and low RPM and start building up the shape of our table. But here, I just want to show you the process that we're going to apply to a single cell. And of course, once you understand this process, you can apply it to every cell. So let's get our engine up and running. All right, so we've got our engine up and running here under steady state conditions. We are central in that cell that we're interested in. What we're going to be doing during the course of this tuning is we're going to be watching our little target here, making sure that we remain as close to the center of this cell as possible. The reason for this is if we start moving between cells, obviously that's going to influence the torque in and of itself. Plus, we're also going to end up with inaccuracy caused by interpolation between the surrounding cells. Before we get started, it's just worth mentioning here that we can see that already we've got a positive short-term fuel trim. So we're actually adding around about 11% fueling even here with a 0 degree cam target in order to get us to our air fuel ratio target of 14.7 to 1. So we're going to be taking note of our short-term fuel trim as we go. Let's head over to our dyno. We've got a torque optimization test set up here. We're going to be logging our torque on the vertical axis here measured by the dyno versus our inlet cam position here being sent to the dyno via CAN from the Haltech ECU. So I'll just make sure we're under steady state conditions and in the middle of that cell now. We're going to click clear and we're going to begin our test. And here what I'm going to do is just advance the timing at 1 degree per second. The cam timing I should say here, 1 degree per second, and we'll see the graph develop. So I'm going to go all the way through here to 50 degrees. And while I'm doing this as well, we'll be taking note of the short-term fuel trim and how that's changing. So let's go through this test and we'll talk about our results in a moment. All right, we'll let our engine come back to idle here and have a look at our results there. So there's obviously a little bit of noise in this graph, and we can do a bit of mental smoothing here and kind of put in a line of best fit through that. What we can see though is that the dyno is showing us here that for that particular cell, 21 degrees cam advance has given us our optimal torque, 334 pound-foot. Now, let's be honest though, with that noise taken into account, we couldn't be pinpoint accurate. We can actually see that from around about 15 degrees there through to probably around about 26, 27, maybe even 28 degrees. We are only seeing our torque change relatively marginally, and again we're trying to average the noise out of that graph as well, but that's given us the peak torque that we have got. We can see that general trend where we drop off either side of that plateau. Now if we were watching the short-term fuel trims while that was occurring, we would also have noticed that our peak fuel trim ended up between about 18.5 and maybe 19.2% positive around about that same point, around about 19 to about 22 degrees of cam advance. So that correlates nicely with what we've seen on the dyno there. So if we're aiming purely for peak torque, peak power, that's all we're interested in, then of course this is the number we'd want to put in that particular cell. We'll want to come back into our cell here and enter a value of 21 degrees. However, let's have a look at our torque optimization test again. And we can see that, again, we've got this plateau that starts probably from about 15 degrees. This might have been a little bit of a outlier actually at 15 degrees, but we can see at least what I'm interested in here is from about 20 degrees through to about 26, 27, maybe 28 degrees. We really don't see much variation in our torque, particularly if we're averaging the noise there or the oscillations in that curve. Now, also taking note of what our short-term fuel trim was doing, it peaked at about 18.5 to 19% positive trim, as I mentioned, around about that 20, 21, 22 degree mark. Actually fell off a little bit to more like about 17% by the time we were up around 26, 27 degrees. So here we can make an educated decision for ourselves depending on what we're trying to achieve. Here, giving up a very small amount of torque can actually give us a small net gain in our fuel economy. So these are the factors we need to consider. In our instance though, we're going to leave our value set to 21 degrees, but our job is not done here. This becomes iterative, as we've mentioned through the course. Now, if you were just making changes directly in your VE table, then you'd be swapping backwards and forwards between your cam timing table and your VE table to get your air-fuel ratio on track as you go. As we've mentioned, we're obviously using our closed loop trim to do this. So now that we've optimized the cam timing here, what we want to do is come back to our fuel main or VE table, and we want to find that same cell that we were tuning, which is this one here, minus 20 kPa and 3000 RPM. And remembering, we're about 18.5 to 19% positive trim. So let's make a percentage change there. We can do this in the Haltech software by pressing the P key, and we'll enter a value of 19%. So what that's going to do is add 19% volumetric efficiency to that cell. Let's get ourselves back up and running in that cell now, and we'll head back to our cam tuning and we'll have a look and see what that's done to our closed loop short-term fuel trim. Right, so once everything's stable here, you can see how quick and easy that was to do. We're not exactly right, but you can see that our trim's sitting at about 1.5 to 2%. So generally I'd be pretty happy with that. Easy enough to come back to our fuel main though. Let's actually add in our short-term fuel trim here so we can see exactly what's going on, and we'll add that channel in. And we can come back up into the cell we're tuning, making sure that we are centered on that cell before we make any changes. And we can make a further change. Let's add another 2% to that. and that should get us pretty close to our target. And again, if I'm within plus or minus about 1 to 2%, I'm going to be pretty happy. All right, so that's got our fueling dialed in for our optimal cam timing, but at this point we haven't talked at all about our ignition timing. Remembering that this is an iterative process. We've got cam timing, which will affect volumetric efficiency, which will affect our fueling, and also to a lesser extent our ignition timing. So from here what we can do is come back across to our ignition table. We know the cell that we're operating in here, and we can apply our HPA 10-step process here to optimizing our ignition timing. It's very much the same as what we've just looked at with our cam tuning. What we're going to do is advance and retard our ignition timing until we're optimal. Now here, what we're likely to find, considering we are already working from a ignition table that is relatively optimized, we'll probably be able to try advancing the timing plus or minus 5 degrees here and see if that gives us a net result of an improvement. So here we're just going around in circles: cam timing, fueling, ignition timing. And if we do see a significant change in our ignition timing, this could be an indicator that we may need to come back to our cam tuning and make a further change there. All right, let's come back to idle here and we'll just talk about what we've learned so far. So at this point, we've used our torque optimization test on our mainline dyno. Now it makes it nice and easy because it gives us that graphical output. Makes it really easy to see that relationship of the torque versus our cam timing. But not everyone's going to have access to a dyno that gives a torque optimization test like that. No problem though, we can use any of the dyno outputs that gives us a torque indication. So here on our mainline dyno, we've got our torque timing graph here. And this is showing our torque in red, and it's showing our ignition timing in yellow. Ignition timing here, we're not going to be overly worried about, but let's get ourselves up and running here, and we'll go through the same process of optimizing our cam timing using the torque time graph instead. Right, so before we get started, we're just going to zero out our cam timing again, and what we're going to see here is that because we've now reduced our volumetric efficiency, remember we made that change to our volumetric efficiency table to get our fueling correct. Our short-term fuel trim's now gone negative, so it's pulling fuel out. All right, let's look at our torque graph here. This is a little bit trickier to do because, as you can see here, even under steady state conditions, we've got quite a lot of oscillation in that red line on our graph. So we're going to do a little bit of mental smoothing here. And in this instance, I find it easier to start by making coarser adjustments. We're not going to really see a significant effect on our torque graph like that by making a 1 degree change in our cam timing. So what I'm going to do is I'm going to start by making a change of 5 degrees. So 5 degrees should be enough to actually see a significant effect. So we've made that change of 5 degrees, and you can see that red line starts to trend upwards, which is a good thing. This means that we've made more torque. So making more torque is just like tuning our ignition timing to MBT. If we are making more torque, we're simply going to keep going in that direction. We'll make another 5 degree step, looking at our red line on our dyno before and after I press enter. Once we press enter, we lock in that change, and again we see our torque increase. A little bit of oscillation there, but once it settles down, we can see that we're still clearly above where we started out, so we're moving in the right direction. Again, looking at our short-term fuel trim, because that's our other metric to guide us in our changes, and we can see that we're still negative, but not as negative as we were when we started our test. Let's go again. We'll enter a value of 15 degrees. Looking at our torque graph before and after I press enter, once that cam tuning change takes place, we can see that our torque has increased. Not significantly there, and this does get a little bit tricky with our cam tuning. Sometimes we are chasing relatively small changes. I'll just make sure I'm back in the center of that cell, and I am. Once we're central in the cell, we can see that yes, we definitely have poked up a little bit. And again, just to give us a bit of a sanity check here, our short-term fuel trim is increasing as well, less negative than it was. We're still going in the right direction. Let's try another 5 degree increment change. Again, I'll just make sure I'm central in that cell, and I am. Looking at our red line before and after I press enter, and really, we're not seeing much of a change here. But remember as well that we were pretty much on a plateau here, even in our torque optimization test. We have actually picked up a little bit, which is what we'd expect, but it hasn't been significant, and this can get a little bit trickier when we are using a torque graph like this. So let's go another 5 degrees anyway. We'll get back in the center of that cell. We'll go for 25 degrees. And now we've actually seen our torque drop away. Not massively again, and we're operating around that plateau as we've already talked about. Let's try 30 degrees, so now we know we're going too fast, so we're expecting our torque to drop away. Let's do that, press enter, and again we do see our torque drop away. They are small changes that we're looking for, but between using our torque graph there on the dyno and then using our short-term fuel trims as a sanity check, this will guide us in optimizing the tuning changes. Now what we will also find though, we're looking at one cell on its own at the moment. Once we start building up that table, we're going to start to see a trend emerge. And just like tuning our fuel and our ignition tables, that trend is going to be our friend. What we're going to do is extrapolate that trend into the next cell. So for example here, we started with one cell in isolation, minus 20 kPa, 3000 RPM. What we would then do is move up in our load. So we'd move up to 0 kPa, and I'm going to know that there's a pretty good chance that our timing at 0 kPa is going to want to be pretty much the same or slightly more advanced than what we saw at minus 20. We know at minus 20 our optimal value is actually 21 degrees. So what we can do is extrapolate that up to 0 kPa, and that's going to get us pretty close to the ballpark before we get started. So in this way, we're just speeding up that tuning process. From here, it's just a rinse and repeat. We're just going to be going through, starting from low RPM and low load, optimizing our cam timing. Then we're going to be increasing our load until we're up to wide open throttle. And then we're going to be increasing our RPM to the next RPM row and repeating the same process. Always looking for our optimal torque, and paying attention as well if we can sacrifice a little bit of torque with an improvement of fuel economy. Sometimes this can be a beneficial exchange to make, particularly for a street driven car.